A little video on the simple mechanical system. That's just a spring and this wheeled cart, and we're going to assume that it's frictionless, so it just moves back and forth, and the only force enacted upon this is the spring itself. Alright, so if the spring is the only thing that's acting upon it, we can use Hooke's law in the force format, where we have force over here, which is usually, if you think about it, weight under Hooke's law. K, of course, is your spring constant. We're going to make the spring constant to be positive. And x is your distance or your displacement from a normal situation where we just have it at rest. So at rest, I'm making 0 where the beginning of the cart is attached to the spring. And if the cart moves in this direction, then we're going to be talking about positive x values. And if the cart is pushed in this direction, then we're going to be calling the x values negative. And one thing to notice is if we pull the cart away in this direction, away from the stability situation, we extend the spring, the force is going to be wanting to go in the other direction. So we have the force trying to go in this direction when we pull it in that direction. So in this case, force would be negative because it's going towards the negative x-axis. And that's true because x is positive, we know k is positive, and we choose this to be negative, so the force is the correct direction. Alright, if we squish the cart into the spring and condense the spring into a smaller space, then the force of the spring is wanting to go in this direction. And this still works out with this formula rather well, because when we condense the spring, x is becoming negative, k is positive, and a negative times a negative is a positive, and F in this case, the force, is going in the positive direction. It's trying to push the cart back to the right. Alright, so that's just the basic setup of a simple cart, and with the one force enacted on it. In this case, we're going to call it force sub S, for the force of the spring. Now there's a few other things that we could do to it. We can put this dash pot on it. I always think of it like on those screen doors, the little compressor, or you can think of it as the shock absorber of a car, the inside cylinder, and the spring is on the outside of the cylinder. So again, if we force this cart, if we just kind of move it very slowly one way or the other, the dash pot's not going to have much of effect. It only comes into play when you push the cart really fast in one direction or pull it back really fast in the other direction, and that's when the force of the dash pot becomes really prevalent. So the force of resistance from the dash pot is going to be based on the velocity. How fast is it moving in and out of the cylinder? So this is going to have another constant. This will be the constant of resistance of the dash pot. Weird name for it, I know. And again, C we're going to consider 0. And we're going to make it negative, because if you're going really, really fast, your velocity is positive in this direction. The dash pot's going to be pushing backwards. So the force of it is going to be opposite of the velocity. And if the velocity is going in this direction, away from the dash pot, it's going to be trying to hold it back, and your force is all of a sudden going in that direction, so it would be positive. So if you have a positive velocity, the force is going against you. If you have a negative velocity, pulling it away, the force is going to be going to the right. So these two are the general setup of what's going on in the dash pot system. Of course, there's an overlying law that enacts itself upon all physical motions. That's good old Newton's law of force equals mass times acceleration. And this is going to be our total force altogether. So we know that Newton's law enacts itself on everybody, and the sum of these two forces plus a possible external force, but we're going to ignore that for now, is all of the forces that add up to this motion's behavior. So we're going to have Newton's law is equal to the spring constant plus the force of resistance. Alright, so that gives us, let's see here, Newton's law is equal to the spring force plus the force of resistance plus possibly an external force, but again, I just want to ignore that. Now Newton's law is ma, force equals ma. The spring is negative k x. The resistance was negative cv. Now these are all different letters, and the m and the k and the c are just constant, So the a, the x, and the v, we really wanted in terms of one variable. Well, acceleration along the x-axis is really the second derivative of x. So we're going to get mx double prime. Then we got their kx, we can't do much with that. And v is the first derivative of x along the x-axis, so we're going to get negative cx prime. So that gives us a nice little differential equation. Now the normal setup is the second derivative, the first derivative, we'll move it over to the left-hand side, and the function by itself. And in this case, this is the homogeneous setup. If it was the non-homogeneous setup, we'd have some f of t here, or f of, well, yeah, in this case it would be f of t. And that would be some kind of external force, pushing it a little bit more, like, if someone's on a swing and you give them a push, it changes the system just a bit. So this is the general equation of a simple mechanical system with a spring and a dash pot. Now generally what happens now is we divide by m and we create these two new constants. You can call it a and b or p and q. It really doesn't matter. But what I want to talk about next is what are all the possible motions that come out of this. Now one of them is if you let c equal 0, take away the dash pot. What happens is the motion of the object, since c is equal to 0, we're going to have some kind of x double prime plus qx is equal to 0. This equation has a solution that is imaginary because q is going to be positive, and when we have an imaginary solution we get the sum of sines and cosines. So the spring would just be bouncing the thing back and forth, and it would, since there's no friction or any other force acting upon it, it would just bounce back and forth forever. Think of it, a spring just going back and forth. So that's one possibility. Very rarely happens because there's usually some other force being acted upon it. The other possibilities are if we extend the formula a little bit and we talk about m, c, and k all being there, all being positive. There are three different types of situations. One of the types is if you have two rational or real solutions to the characteristic. That means you'll get something like e to the r1t and e to the r2t. So that would give you two e functions where r1 and r2 are not equal to each other. It would be the sum of them with some constants, and that would equal, well, in this case, our x function. Where's undo? Our x function. So this would be x of t. Now this would just be two e functions. No matter what you put in for t, this whole thing is never ever going to equal 0. So that gives us a graph that looks something like this. And it just kind of comes down and it eventually gets back to where it belongs. This is called overdamped. Overdamped. This is where the damper is stronger than the spring. And if you're talking about like a shock absorber in a car, it's when you hit a pothole and you feel it. And the car, the tire, if you want to think about it, jumps up to this position and then it shoots back down to normal without going past any, safe cushioning zone. So this is a very, very stiff shock absorber. The other possibility is what if we talk about a double root? No, let's not talk about a double root. Well, let's talk about imaginary roots or complex roots. So we get r equals something like a plus or minus bi. And again, we only really want to concentrate on the plus part. The negative one gives us similar answers, and they're not double roots, so we don't have to worry about them. Here we're going to get some kind of x is equal to e to the at, and then some coefficient of cosine bt plus some coefficient of sine bt. And this one is kind of interesting in the fact that we have the sine and cosine going on, so we're going to have some kind of wave from that. But then we have this thing out front controlling it, and if it's working right, this would be negative at. It would be some kind of negative number. And that'll control the behavior of the sine and cosine. And what happens is you get a graph that looks like this, where your e to the at's graph is a descending exponential, and it kind of controls the amplitude of the sine and cosine. And this is more like a very weak shock. Have you ever seen a car hit a bump and it starts bouncing up and down like it's on a spring? That just means their shocks are going bad. The dash pot is not as strong as the spring motion. Also, if you have like one of those swinging doors at a restaurant, this is kind of the behavior that it has. It swings wide open, and then when it shuts, it kind of just vibrates back until it's closed. This is called underdamped. And underdamped motion just means the spring is stronger than the damping device. Now, neither of these are the best for shock absorbers on a car. To get the shock absorbers to work right on a car, we need the possibility that the roots repeat. Then you get some function that looks like this. You get your RT, and your root is going to be negative. Plus, and then since it's a repeating root, you'd have to include a factor of t. And what this does is it makes the motion rather nice. And the reason it does is because t can become negative, so you can pass through the x-axis and go in the opposite direction just a little bit and have a nice smooth return to normal. Now the graph of that looks something like this, where your tire gets yanked up a foot and then it smoothly comes back and gives you a little bounce in it. So it might go through and then come back up. And it's a little bit smoother motion than the critical damping. Wait a minute, not the critical, the overdamped. This is called critical damping, where you have repeated roots. And this is the one you aim for if you're designing a shock absorber on a car. You want a nice smooth return to where you were. That's it about simple motions with a dash pot and spring.